All right, we'll go ahead and get started. A few adjustments there. I'm used to walking around, so I know I need to stay here or the volume's not going to work. So we'll see. I might get fidgety and start walking anyway. It's hard to say. When I was looking at Zen and KVM sort of items when we were working out earlier this year, one of the things that this conference provided was a end user type of talk. So I submitted my abstract and said, let's see how it flies. Oh yeah, yeah.
Power's on top.
Yep. That's what I'm used to. Perfect. These always work a lot better for me. So one of the talks types that they had was a end user type of talk. So I was like, okay, perfect. So I'm not going to tell you or profess to know everything there is to know about Zen for sure, but I will tell you a little bit about how we're using it. Yeah, GE Transportation. So a couple disclosures. Anyway, the agenda we're going to go through is I'm going to talk a little bit about the Locomotive System. We're running Zen as a hypervisor on locomotive units running around the field. By the way, both GE and non-GE locomotives, which is kind of neat. We're going to talk about what our use cases are for virtualization, go over our hardware platform, and then most importantly, which is kind of towards the end, is discuss what's important to us in virtualization. So if you're a developer for virtualization, or maybe a co-developer or a co-user just like me, you can kind of see what sort of attributes that we're using for it. And since time has been cut short, the other one ran over by 10 minutes, there's zero chance I'll be able to do a demo. But I'll at least show you the hardware. That's all I can do. A little bit about GE Transportation. I'll do this slide quickly. You can read. GE Transportation is all about locomotives, primarily. We do have some other niche markets that we work in that you can see there. Our world headquarters is in Chicago, Illinois. It moved there about 3 years ago. Our original headquarters was in Erie, Pennsylvania. It's actually one of the 3 oldest GE facilities that exist. The first one, I believe, was in Schenectady, New York, and then our transportation, which builds locomotives, came around third, and it was in the early 1900s. So GE Transportation has certainly been around for a long time. These are the sorts of markets that we work on. I'm a part of the your upper right-hand quarter, which is called Intelligent Transportation Solutions. So we work on products that basically help automate the railroad. So you can think of locomotives as kind of big chunks of iron. Easiest way I describe locomotives, it's a portable power plant. It's literally runs a diesel engine and it generates power, and we use the power to connect the traction motors, but if you wanted to export the power to other devices, you certainly could. It's basically a portable power plant on wheels. But there is certainly a lot of technology involved with that. Our railroad customers, because of the consolidation that's happened in the industry, there used to be railroads called like Monon or Chicago Northwest. All of those have basically been consolidated into 7 railroads in the United States and Canada. So my customers, I have 7 for the most part. I do have some worldwide customers too in Australia and Brazil and South Africa. But for the most part, I have 7 customers, which is kind of unique. I can get involved with them and understand what their data plans are. But moving freight is extremely important for them. Outages, stoppages, et cetera. I had one customer tell me that every time a train stops on a particular piece of track, and it was actually a very high priority piece of track, the cost of the delay was right around $20,000 per minute. So they do not tolerate delays, and they definitely are looking for more automation in their products. A little bit of background about me. I work for the Cab Electronics group for GE Transportation, primarily just onboard automation and electronics. I actually am based in Melbourne, Florida. The original reason for that is because our business unit used to be a joint venture between Harris Corporation and GE. And Harris Corporation's in Melbourne, Florida. So that's the reason why I'm basically based there and our group's based there. I'm a product architect. I primarily work on wired and wireless communications, develop different protocols, et cetera. One of the protocols we developed and actually submitted to the industry allowed basically an operator to have a handheld unit and work in a rail yard and remotely control a locomotive. So there wouldn't be anybody on board the locomotive, but he could actually use the handheld unit, and it was a lot safer. So instead of telling somebody over a radio, hey, you're getting ready to couple, one car, half car, stop, he could basically control it himself. So it was a huge safety play. Accidents went down, et cetera. But basically, it's the wireless communications now with a box locomotive. Obviously, those sorts of things need to be secure, and everything as far as stopping and not hearing communication needs to be automated. Believe me, before the last guy ran over as much as he did, I was a huge ARM fan. No, I'm just kidding. I'm still a ARM fan. GE is migrating a lot of our processor products. Because we're kind of an older technology, we tend to keep using things if they work. I mean, certainly we had a lot of PowerPC designs, even some older TI designs, but we're slowly migrating a lot of our stuff over to use ARM. And then Linux is also a huge, important operating system for us as well. So a lot of the things I talk about, how we use Zen, hypervisors and things like that, just know that I'm coming kind of from a Linux ARM sort of background when I talk about them. So quickly about the locomotive system. Again, it's a power plant on wheels. Diesel engine basically generates power. The power basically goes to the traction motors. There has been efforts in the past to make hybrid locomotives. GE is still working in that area, but the problem is that the battery technology is key, right? We generate right around 4,400 horsepower, and taking all of that power and putting it into batteries and then somehow going from the batteries to the traction motors in a very hot environment, very difficult. Again, we're still working in that area, but since I'm in Seattle on the West Coast, I figure I'd mention that we do that sort of hybrid technology. It's just not been perfected yet. The items that I primarily work on are going to be up here in the front, in the cab. I'm going to pose it, if you've ever seen a locomotive train run and it has maybe a couple locomotives in the front, then there's a whole bunch of rail cars, and then there's a locomotive like in the middle or at the end of the train. I don't know if you've ever seen that before. GE, that's part of one of the things that we do in our group in Melbourne, Florida. It's called distributed power. So there is nobody on board that locomotive there in the back. It's not wired, because you can't run a wire that long and it'd be difficult to try to maintain. That's all wireless control. So it helps because now you got locomotives pushing at the same time you have locomotives at the front pulling. So instead of having a huge amount of drawbar force between the last locomotive and then your cars, you can basically distribute it, saves fuel, saves wear and tear, et cetera. So that is one of the products. That is what's considered a cab electronics product. Another product that we have, I'm again giving you background for the reasons why we would need virtualization. Another one we have is actually cruise control for a locomotive. The train engineer places it in cruise control. Obviously, he's still in control, so if something goes awry or something's not right, he can take control. But we know the makeup of the train, what's on every car, how much the car weighs, the length of the car, and we know the entire track topology. With that information, we know exactly what to power each of the engines or apply brakes so that we can basically cruise through the system at a certain speed. Okay? Further complicated by sightings and things like that. Obviously, you don't know. Think of it like this: if you leave a stoplight and there's another stoplight, you're not cramming on the accelerator to go as fast as you can because you know you have to stop again. You're probably going to coast a little bit, and we have that sort of technology built in as well. So that's another product we have called Trip Optimizer. I'm going to show you a video because one of the things I want to stress about all the automated systems that we do, whether it's Trip Optimizer I talked about, knowing the train's makeup, knowing its weight, et cetera, or things like distributed power, knowing that we can wirelessly communicate with the trains. For us, I mean, one of the things I always say is it's all about data. And it becomes very important. This is probably a good volume. It doesn't need to be that loud. You guys don't need to hear horns. This is a video which is interesting. This is nobody's died. Okay, I gotta say that up front. You're not gonna see any death here. But we're basically moving along a train. There's a lot of data going on. We know our speed. We know what the signals are. Everything actually at this point is good. But the problem is we're coming to a siding, and the train that you were getting ready to see there has lost its air, which means the person that's on that train has, we call it pissed away their air, but gotten rid of all their air, so he cannot stop. So he is now moving at a very slow speed, and in fact, you're going to see him jump off because he knows see, he just jumped off the side. These trains are going to hit. Okay, camera didn't make it, not a whole lot made it. Basically, a locomotive's $1 million plus. Okay, so that's a bad accident to have. The thing is that with data, we know that that locomotive is out of air, right? We know he's moving forward, we know his speed, we know his location, we know that we're going to hit. What sort of technology can we pull in to actually make it stop sooner, put on our brakes, et cetera, so maybe the collision like that doesn't happen. This one's actually a little bit more clear. This one's just dumb luck. It's not even dumb luck, it's a poor driver. He's assuming the type of meat he has because he sees the train sitting there on the siding. He thinks he's actually going to go straight through and then stop and then let this other guy pass. He doesn't realize that the track is actually aligned to go right into the back of this car. And the thing is, the track knows it, he knows it, now he knows he's in big trouble. By the way, you see that what looks like aluminum foil? It's a quarter inch plate steel. It looks like aluminum foil because you have that much weight hitting a cars like that, it just turns into a big mess. So again, for us, what sort of things can we do, again, with hypervisors, collecting this information, making interpretations becomes really, really important. So now let's talk a little bit for us about, I don't know, let's call it the way that we kind of think. So, if we want to process all this information, whether it's alerts, messages, data, et cetera, one of the things that we do in the past, as soon as we have a great idea, we'd go and add a box, we'd go and add a cell modem, probably a GPS, and we throw it on the locomotive. That's exactly the way we always used to do it. So we would go in and pick this processor here based on whatever need we had right then and there. Okay, we want an app that does this. We want an app that just reports position. We want an app that looks out for signals. And we'd go and basically fill up the locomotive like that. Two things. Number one, the roof of a locomotive is huge. You can fit as many antennas up there as you want. If you need more GPSs, just add them, there's space. Second, locomotives don't care about weight. Okay? Locomotives typically add weight so that they're heavier so you have more traction for your wheels. They'll add extra steel just to make them heavier. They don't care about weight. And power, we're a power plant. We got plenty of power, right? So if you look at that just from that standpoint, it's like, yeah, add a box, add a box, add a box. But the thing is that once you start thinking about it and you start adding this disparate boxes, well, how do you make all these boxes talk together? So you got box 1, box 2, box 3. Maybe the first thing you do is actually go and consolidate some of the wireless or GPS technologies. And then eventually you get to a picture that kind of looks like this. And in fact, I don't know if anybody can see it. I'll kind of hold it up. This is our standardized platform now for our cab electronics that comes out of GE Transportation. I will talk about this here in a little bit, but this is basically what we call our mobile data center. And I'll pull a couple of cards out and show you here in a second. So it's kind of like a different way of thinking about things. So instead of having a bunch of disparate boxes, now we can have our own applications basically running on that platform. So what does that mean? Well, we've got guys that write stuff in Windows. We've got guys that write stuff in Linux. We've got guys that write stuff in a different version of Linux. So you can see if we want to all run in the same hardware, virtualization for us becomes really, really important. So some use cases. The first one is kind of the problem we started with, right? We always typically picked hardware, we picked an OS, we picked an application, and put it on this thing called a black box and put it on the locomotive. Obviously with virtualization, one of the things we can start doing, as I just showed in the previous slides, is you can start collecting applications in OS and putting it on hardware. So start commonizing our hardware, and that's kind of the first step that we did. The second is that we can start thinking about how do we have maybe some trusted instances, and how do we have things like high availability? One of the things I can tell you GE struggles with whether it's Zen or any hypervisor is this whole thing about high availability is how do we manage applications so that this application must run? And if the temperature of the box starts going up, okay, we want to run this app, take away a CPU core, move it over to this other one. We need to have some of those sort of dynamic tools built in. So a lot of the work that we're doing right now has to do with high availability. And I'm not going to read the slides in interest of time, but they are uploaded to the website so you can download them. Next one is running legacy software. We certainly don't want to have to go and rewrite a bunch of software. So we do like the model that Zen and KVM have, that we can actually have our own OS without having to share a kernel or sharing an OS. And we need to go and just create and destroy virtual machines as needed and necessary. We'd like to run virtual machines like a maintenance one when we're in a yard and then shut it down when we leave the yard. So use some geofencing and things like that. Trip optimizer, the one that I talked about that basically drives the train itself, uses a lot of resources up front to go and plan the trip, quote unquote plan the trip of the profile it wants to take. And then again, we can take away virtual CPUs from it and allocate them to other places as we need to. The other thing that we'd like to do, and we haven't gotten there yet, but we're working on it, is actually dividing our applications up to be things like that I showed there, data plane and control plane. So maybe as balances of collecting items for a data lake come up, we can allocate resources there, or move them over to control area if for some reason we're moving or we're in a critical situation. Just as kind of a summary of the different use cases, the one I do want to mention that I think is really important for us is what I'll call sandboxing. Right now, GE, and I'm sure it's the same for any automotive manufacturer, when we want to release a new software package, because these locomotives, we literally might install it and never see the locomotive again for a couple of months, it's got to be solid. It's got to be right. It can't be something we have to go and try to chase down the locomotive and touch and update. So for us having this capability of doing sandboxing where we can have an application actually install it and get some runtime, even if it doesn't work. Maybe it crashes every 15 minutes. But the data that it does collect, we can actually feed back in, maybe even the logs, to help our development get it out in the field quicker. That's a whole concept we call sandboxing. So we love virtualization engines like Zen so we can actually go and try things out before we actually formally release it. So hardware platform, I did say that I was going to talk about this. That is our hardware platform. It is basically, I'll just slide one of the cards out, and I'll explain the cards here in a second. But basically, they're very, very ruggedized processor cards. So the one that I just pulled out here, this is a Core i7. Okay. Now, one of the things you'll notice about it, there's no fans. So our customers hate fans. They don't like fans. They're a nuisance for reliability and having to update and keep track of. So we put a lot of science and engineering into our heatsink design using some fairly advanced materials. So we can actually run a Core i7 without a fan. We also try to use standardized things as much as possible. You can see the mSATA drives in the back. There's actually 2 of them. We can stack up 2 of them. So this is pretty much a typical processing card that we have. Pooling is huge for us. We like to pool our resources together. So if you can see my chassis, some of you can't, but I did hold it up. There's another one exactly the same as this card right next to it. So if I had a chance to do the demo, I'd show that they're basically pooled resources. I start operating systems, and it basically runs on either one. The other one I'll show you, it's kind of sitting next to it. I'll go ahead and pull one out. This is what we call our network storage device. So these are our drives, basically a massive heat sink. These drives heat up really, really hot. This is an SSD-based technology design. This is 4 terabytes. And there's one right underneath that one that's another 4 terabytes. So it's basically 8 terabytes. What this allows us to do, though, is all of our operating systems and everything can be installed right on these. So when we go and launch an operating system, it basically can run right off of here. Okay, so it's kind of nice. It's also kind of an upgrade path, or if we need to get critical logs off a locomotive, we can do that. So there's 2, and there's RAID technology and things, so you can mirror things between them if you want, etc. So from a platform standpoint, again, we're just looking for simplification, reduce costs. We don't have to have a whole bunch of boxes. It does help free up some space. Believe me, as soon as you start having a lot of electronics boxes, it does start taking up some space in the locomotive. And then again, as I mentioned, with the pooled resources, redundancy becomes important as well. So let me talk to you a little bit about what we're using for our network-based cards in our chassis. I'm going to divide up in 2 different ones, 32-bit. If you were here for the ARM presentation right before me, we are using, for our 32-bit, the ARM v7A with the virtualization extensions. So we're using a Cortex A7. The one we're using is a Freescale LS1021. It's called their Layerscape 1 part. Very nice processor. It was built for networking. It has things like ECC on the internal bus, which is fantastic for us. So it keeps our data integrity extremely quick. But we tend to go ahead and choose a processor based on interface need. The Layerscape 1021, by the way, is the process that actually runs our networking storage that I just pulled out. So that's the exact same process that we have for that. 64-bit, we are looking at that. Right now, they're a little bit too high power for us, too much heat for us to shed. And I will tell you, it's kind of the cliff note down there at the bottom because we've ran into some issues with Zen on ARM, especially with the Layerscape 1021 part. Right now, we're using KVM for that particular processor card. So I'd be more than welcome to talk with anybody about that to see if we can fix that, because I hate supporting both. We do use Zen, though, on our Intel-based platform. The first is an Intel Bay Trail processor. It was released in the fourth quarter of 2014. It's labeled as an Atom because they didn't want to market it separately, but its architecture is certainly a lot different than Atom. It's called an E3845. It's quad-core running at 1.9 gigahertz. A lot of the virtualization extensions that that particular processor has was borrowed from the Core i5. So it's a really, really nice industrial-based junction temp of 110. Our processors, especially with no fans, we're usually running right around 92, 94C. Our RAM usually gives out long before our processor does. We call that our starter set. So if a customer comes along saying that they'd like to have an application board, that's typically the one that they'll start with. The high test one you can see there is a Broadwell. The silicon was released in 2015. The designation is 5500U. It's a dual core, by the way. I think, even me, I was used to i7s or quad cores. This one's a dual core, because again, we don't have any fans, so we need something that's a lower wattage. I think it runs right around 14 watts. Our Intel Bay Trail runs around, the processor runs around 6.5 watts. So you can kind of get an idea of the difference between the two. Another slide, I had to throw this one in. Don't want to start a holy war. But the other thing we've started getting involved with a little bit is Linux containers. The reason why we did is because whether it was Zen, which we couldn't get working, or KVM on our 32-bit processor, it just ran like a dog. It wasn't fast enough. I mean, it's an 800 megahertz dual-core processor. It does have DDR3 memory, but it just didn't run very well. So it got to be kind of a pain in the butt. So what we ended up doing is started looking at using Linux containers, again, on our 32-bit platform. So we've looked at LexC, LexD, and then even looked at things like Docker and Rocket for our applications. One of the demonstrations I was going to show you, we actually run Zen, then we run Ubuntu in Zen, and then we ran LexC, LexD in that instantiation of Zen in the guest, and then we ran Docker and Docker on top of that. So I actually see application for all these possibly even running at the same time, because we do like to have separation of our apps. It would be nice to have separations of our OS, and when needed, if we need to run Windows 8, Linux, et cetera, all at the same time, we want to have that capability as well. This is a kind of a poor graph, but again, this is opinion, so you can say that I'm wrong, but this is kind of what our current stance is. So for our Intel platform, we're basically recommending to our customers and our developers Zen all the way. For that, you can see a little bit of KVM kind of thrown in there, but it's been difficult. Intel Zen seems to work really, really well. We did run into difficulty again with ARM 32-bit. KVM doesn't run that well, so we're kind of recommending, hey, you might want to look at this LexC, LexD thing for containers. And then the whole frontier, I think, is the 64-bit. I did circle the Zen one. Our opinion can change, certainly, if support's there for the 64-bit chip that we're using. We don't want to try to, we don't want to have to support two. We don't have to. I'd rather have our developers participate in one, because otherwise they're going to start confusing them, right? Oh, I heard you could do this to get Zen working. Well, no, it was for KVM or something. It'll just turn a confusing mess. So we will reassess that when 64-bit for us comes around, which will probably be late next year. We're waiting around for a new networking part, and it's not going to be available for silicon. It's going to be in the second quarter of next year. So that's when we'll make our assessment then. But that's just my opinion. Nobody's throwing things at me, so I guess that's a good thing. Couple of last slides here, so I can get done here on time. Actually, I'm 2 minutes over. I don't want to screw up the next guy. I did want to put a couple of slides together what we think is important. Number one for us is Zen processor support. We have definite use cases where we want to be able to add new processor cards in the future and have them be as the same pool of resources. So I want to be able to have a Bay Trail and a Broadwell running side by side and be in the same pool, so I can just throw applications at both of them and they just run. Because if I think of it long term, as I add locomotives to the pool and new processors come out, I don't want to necessarily just have to yank all my processors that I have. I always just keep adding. Oh, you need more processing capability? Here's more processors. So that's extremely important that we have support for those processors. Second is local management of guests. I'm having some personal issues with this one, trying to define this. We'd like to be able to add stuff in the hypervisor that basically has automatic restart of guests, maybe monitor it. You know, is it doing the right thing? I mean, I hate to add too much application stuff in, but have some sort of capability where we're actually checking to make sure our software is doing the right thing. And also, you know, pool management. So if a processor starts to get too hot, maybe he can automatically start shutting off some guest operating systems to the other cards in the system. And just have it all happen automatically so our customers don't have to fool with it. And last, I know that this one's probably easy to fix, but the way that we manage locomotives is we treat locomotives the same. They're not separate. They'll go and read what their locomotive ID is, but from then on, we don't want them to be separate. So operating system, guest OSs, hypervisors, I want to be able to just take and move direct from one to another seamlessly, right? I know it's probably fixable. We've certainly had some, you know, UUID things where we tried to copy stuff over and it didn't work. See, the thing is, we're not looking for that because we're trying to manage all of our locomotives as a fleet. So, you know, being able to move stuff around, card breaks, they're literally going to take one card out and put a new one in, and it just needs to work. You know, seriously, no loading, no nothing. Maybe we're using Pixie Boot to grab stuff off our network storage or whatever. But there's a lot of, you know, basically the cards that we're going to be deploying need to last 10 to 15 years when they're in the field. All right, well, there's a picture of my demo we don't have time for. But again, you know, we had some Bay Trail processors. We have a Broadwell. You can kind of see Zen here, ran in Boot 2, ran Linux containers on top of that, and then you can use, you know, any of the other application containers on top of that as well. So again, I appreciate just kind of the opportunity as an end user, kind of telling you a little bit about how we plan to use Zen. Hopefully you learned a little bit about the railroad. So with that, I'll open up just for maybe one or two quick questions, if that's okay. Yep.
Can you describe your split between architectures on ARM and x86? What percentage is it?
Yep. So right now, with 32-bit ARM being the most prevalent, when we do applications development, which basically means not connected to specific hardware I/O, it goes Intel. As soon as it has something to do with, maybe we have some RS-422 synchronous, maybe we have a vibration sensor, things like that, those typically start to move more towards the ARM space. I expect as we move forward in the future, for us, Intel will probably phase out a bit as soon as ARM 64-bit's available. Because I see 64-bit and Intel kind of having the same processor class as far as being able to crunch a lot of data at the same time. So I kind of see that shift happening. So maybe right now for our applications, we're 30% ARM, 70% Intel, and I expect that to shift probably the other way around in 2 years. Any other questions? Okay, I am available, and I appreciate you guys attending. So have a great conference. Thank you.